Hello everyone. Let us solve some numerical problems based on Laplace equation. In this question, it is asked to determine whether or not the potential function satisfy Laplace equation. First, let us understand Laplace equation is del square v equal to 0. This del square v can be written in each of the coordinate system depending on the potential function. Let us start with the first subdivision. In the first subdivision, the given potential function is given in rectangular system of coordinates. So in this, we have to write del square v in rectangular system. In rectangular system, this is given as dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square. These are all second order differentiation of the potential function v, where the given function v is 2x square minus 4y square plus z square. Now, by checking this, whether the Laplace equation is satisfied or not, we should first find del square v and check whether it is becoming 0 or not. If this becomes 0, then we can say this is satisfying Laplace equation. Else, we can say the given potential function v doesn't satisfy Laplace equation. Let us work out and find whether the given potential function v satisfies the Laplace equation. So del square v can be written as, this second order differentiation can be written as 2 times differentiation of v with respect to x, y and z. So let me write first 2 times differentiation with respect to x and second order differentiation of this potential function with respect to y. And similarly, we can write the second order differentiation with respect to z of this function, which is 2x square minus 4y square plus z square. Now let us do the differentiation of this. Differentiation of this first time with respect to x will give 4x, and the second and third term differentiation with respect to x will be 0. And again, this one differentiation with respect to y will give minus 8y, and this differentiation with respect to z will give 2z. Now, this has to be differentiated one more time with respect to x. This has to be differentiated one more time with respect to x. That 4x has to be differentiated one more time with respect to x. And this minus 8y has to be one more time differentiated with respect to y. And this 2z has to be one more time differentiated with respect to z. So let us perform that. So that is going to give let me continue with this. So del square v equals, so 4x differentiation with respect to x one more time will give 4. And this minus 8y differentiation with respect to y will give minus 8. And this 2z differentiation with respect to z will give plus 2. So this becomes 6 minus 8, which is minus 2. This is not equal to 0, which says del square v is not equal to 0. Therefore, the given potential function v does not satisfy Laplace equation. Now, similarly, we have to check for the other two in the other two coordinate system. For subdivision B and C, we will do similarly. So for subdivision B, this is in spherical system. So we have to take the formula for del square v in spherical system to solve for this. So let me write del square v equals to 0. This is the Laplace equation. Now we should check whether the given potential function v satisfies the Laplace equation. So let me write del square v in spherical system formula. This is in spherical system 1 by r square dou by dou r of r square dou v by dou r. Then 1 by r square sine theta dou by dou theta of sine theta multiplied with dou v by dou theta. Then 1 by r square sine square theta dou by dou phi of dou by dou phi. So second order differentiation, I'm writing 2 times here. So now this potential function v is r square cos phi plus theta. And this potential function v is r square cos phi plus theta. And this potential function v is r square cos phi plus theta. Now we should do the differentiation and check whether the given potential function satisfies the Laplace equation. Let me write del square V 1 by r square dou by dou r of r square into what is the differentiation of this with respect to r, we will write. So that will become 2r cos phi plus 0. So it will be r square into 2r cos phi. Then the second term will be 1 by r square sine theta dou by dou theta of sine theta into differentiation of this with respect to theta. So differentiation of this with respect to theta. First term is 0, second term is 1. So it is 1. And the third term, 1 by r square sine square theta. First order differentiation with respect to phi of this term will be r square. Differentiation of cos phi is minus sine phi. So minus r square sine phi plus differentiation of theta with respect to phi is 0. Now this has to be differentiated one more time. The second order differentiation has to take place here. So let me write the second order differentiation. This has to be differentiated with respect to r. So we can write this as 2r cube. This can be written as 2r cube cos phi. Now we can try to differentiate this. So 1 by r square is the term left. So this differentiation will become 6r square cos phi. Then the second term will be 1 by r square sine theta. Differentiation of sine theta is cos theta. Then this last term, 1 by r square sine square theta. Now this has to be differentiated with respect to phi. Differentiation of sine phi is cos phi. So minus r square cos phi. Now the final expression is going to be this r square and r square will be cancelled. So you'll get 6 cos phi plus cos theta by r square sine theta. Then this r square and r square will be cancelled. It will be minus cos phi by sine square theta. Now this is not equal to 0 and hence you can say the given potential function V does not satisfy Laplace equation. The given potential V does not satisfy Laplace equation. Now similarly we can do the third subdivision also. The third subdivision is in cylindrical system. Let us check whether that function at least satisfies the Laplace equation. So let me write this is in cylindrical system. So let us write Laplace equation del square V equals to 0. Laplace equation in cylindrical system, let me write del square V is 1 by rho dou by dou rho of rho dou V by dou rho plus 1 by rho square dou square V by dou phi square plus dou square V by dou Z square. And we have to find this and check whether that is becoming 0 or not. So let us write 1 by rho dou by dou rho of rho into dou by dou rho of rho cos phi plus Z. Then second term is 1 by rho square dou by dou phi of dou by dou phi, second order differentiation. So rho cos phi plus Z. Then dou by dou Z of dou by dou Z of rho cos phi plus Z. So this has to be done with differentiation. First differentiation with respect to rho we should do. So this will become cos phi. And here differentiation should be done with respect to phi. So rho is constant. Differentiation of cos phi is minus sin phi. And second term Z differentiation with respect to phi will be 0. Now again this has to be differentiated with respect to Z. First term differentiation will be 0. Second term differentiation is 1. So that is going to give 1 by rho dou by dou rho of rho into cos phi. Then plus 1 by rho square dou by dou phi of minus rho sin phi. Then dou by dou Z of 1. So this has to be differentiated second time and that is going to give. So this has to be differentiated. We'll get 1 by rho into cos phi. Then second term is going to be 1 by rho square. Differentiation of sine phi is cos phi. So you're going to get minus rho cos phi plus 0. So this is del square V. Now, if you consider these terms, so this rho and rho will be cancelled. Here you are getting 1 by cos phi, and here you are getting 1 by rho cos phi, and here you are getting minus 1 by rho cos phi plus 0. So this is becoming 0. Means here in this case del squared V is 0. This says the given potential function satisfies. The given V satisfies Laplace equation. I hope you have understood this problem. Similarly, you can expect any function for V, and you will be asked to check whether the given potential function satisfies the Laplace equation or not. Thank you for watching the video.